All right, we touched on barcodes a little bit. You might be surprised of how many different types of barcodes there are. So this is the Wikipedia page for barcodes. And there's a code 25, code 11, code 39, 49, 93, 128. And then there's some European standards. There's Pharmacode, MSI, all kinds of crazy crazy things, and then these new two-dimensional barcodes. Those are fairly new. There's a bunch of kinds of those. Anyway, there's some round ones. There's all kinds of crazy barcodes. So we talked a little bit about code 39 being one of the simple ones, just having ones and zeros as a short or a long, sort of like a Morse code. So let's take a look at code 39. Interesting thing about code 39 is it is alphanumeric, so it is full ASCII. Some of the barcodes only encode numbers. This one does encode letters as well. And you can take a look at, there are the different bit patterns for the alphabet. So these are the things you can code. And it talks about there's a start character and a stop character, and so whether you're going left to right or right to left. So a lot of interesting things. There's one other barcode that, of course, we're all familiar with, and that is the UPC codes. Take a quick look at the UPC, which stands for Universal Product Code. Universal Product Code is just encoding numbers, and it uses more than just shorts and longs. It actually, let's see if there's a good example here. It actually has 4 different widths. It has 4 different sizes in width and for bars and spaces. So let's see if we can maybe tap this one. You can see that there's a narrowest, so those are like units 1. Here's a unit 2. Unit 3s are these fat ones here, and then here's a unit 4 over here. So there's 4 different widths. And this one has interesting start and stop characters. There's a black, white, black, and a black, white, black. It doesn't matter which direction you come from. There's a black, white, black, and then it goes black. Over here it goes white, so you know if you're traveling left or right. So again, there are start and stop characters. And then this one actually has a middle character. It has this black, white, black in the center here that allows you to look at things. So you imagine if you're building a circuit to decode this, you're going to be scanning an analog signal. The analog signal can vary up and down. It doesn't reach full white, it doesn't reach full black. It kind of varies depending on your spot size of light. You may not be able to resolve these things completely, so there may be a small modulation, a big modulation. These things are printed in different colors and different densities, and so you need something that kind of can track things along the way. The other thing is if you have a flying spot, it can actually have an acceleration. It can move slow and then speed up, or it can speed up and slow down, or it can do both. So you have to be able to have some type of software to decode a barcode, and that software has to even out the spacing and make sure that things kind of travel at a constant velocity. That's sort of the first thing you have to do. We won't be talking about the software of decoding barcodes. I wanted to talk about what type of electronics you would use in order to build a barcode reader, and show you an example of that. So this is a photograph of a handheld barcode scanner. It's a pen type. You hold it in your hand, and then you drag it across the printed tag, and it decodes the software, decodes in software. And so all of the electronics and decoding engine and everything is inside of the pen. These originally were developed for the HP calculator. not this particular one, but the pen type version was made for the HP41 calculator, so you could print programs and then load them into the calculator. And then it kind of turned into a product line, and different versions were made. This particular one is a product that I designed, and its claim to fame was it would read the barcode tag, and then this section here was a cable assembly that interfaced it to an IBM PS2. And so when you plugged your keyboard into here, and then this plugged it into the keyboard port of the PS2 computer. And if you scanned a barcode tag, then what it did was it actually pretended to type in the data. And then when it was done, it sent control back to the keyboard. So it was a way to get data into a PC just by keyboard strokes. So let's take a look. Take a look at this. I have some prototypes, original prototypes of this product, and we'll kind of see what's involved in that. So when you design products, you need some way of being able to figure out whether things are going to fit or not. So when we were working on this project, we had some of these plastic cases. So this is the wand, this is the optics in the front, and the cable came out the back. We had some cases made out of clear plastic just for us, and we would use these to make sure everything was fitting in there and everything was working correctly. The final product was either a black or a gray. But we can kind of pop the end open and take a look at the circuitry that was inside this thing. First of all, there's an interesting optics inside this can here. This is the place where we have an emitter and detector and two bifurcated lenses. And so the light goes out to a point and then gets sent back in to a point. So all of the magic of the optics happens inside this can. And some of the barcode readers just had a hole drilled into the case, and you would scan that. This particular one was a sealed unit. It was waterproof, and there was actually a optical port here. It's actually a sapphire ball, and these 2 points of light actually went through the sapphire ball and focused even a little bit further. And that ball, the way that this thing was designed was that the light was focused at the end of that ball, so when that ball was on the paper, it was in focus. And so you could tilt it, but you knew that if you were on the paper, then it was actually working. And it was made out of sapphire because paper is quite abrasive, so you needed something when you scanned the barcode tag, it didn't wear the thing out, because you'd be scanning thousands, if not a million, different barcode tags. So this is the circuitry that was inside this thing. This particular device was what we called a smart wand. Some of the wands were dumb, and all they outputted was ones and zeros. So as you went across the barcode tag, it would just send out 00110101. It would just digitize that. In fact, it wouldn't even send out zeros and ones. It would actually send out the analog waveform. So it would just shape the waveform and send out a pulse train. And then it was up to the circuit outside to actually figure out what a 1 was and what a 0 was, and how to do all the acceleration stuff and things like that. This particular one, though, was what we called a smart wand, and it was able to digitize the circuitry. That's what all this is here. It digitized things into a high-low data stream, and then there was a piggyback board here that had all the microprocessor on it. And the microprocessor would then do that decoding, and this particular device would actually send it out as RS-232 data. So this was a serial interface one. The one that did the keyboard interface we'll look at a little bit later, but this one was definitely the one of the first we ever built that had the actual decoding inside of it. Normally you had to buy a box that had all the decoding stuff in it, and your wand was a dumb wand, and then you plugged it into a box that did all the decoding. But this one has it all inclusive. And like I said, all of this circuitry was required to shape the waveform and get a correct digitization level and things like that. And then this stream of high, low, high, low, high, low was sent to the piggyback board. So let's talk about why all the circuitry. What would be required in order to do that? All right, so we had a barcode tag, and we have an analog output. That analog output is gonna swing up and down, and there might be a wide one, and then it might be narrow, and then there might be a wide one. And so what you want to do is you want to have a threshold that allows this to be a 0, then a 1, then a 0, then a 1, 0, 1. And you can see that if we continued with this threshold going across, we would miss this modulation here. So we really want to have a threshold that somehow is adaptive, and it sort of follows this modulation, so it moves up and down with the signal, and so we're always digitizing correctly. So how do we do that? Well, you can imagine that if we let me draw just a simple example. If we wanted to have a threshold that made it through this thing, if we put in a circuit that's a peak detector, we could have a peak detector that sort of follows the peak, and we could have a negative peak detector that sort of follows the negative peak. And then we could say, okay, well, we're going to take a 50% threshold between those two peak detectors and run that into a comparator. So we can do that. A peak detector sort of looks like this, and a negative peak detector looks sort of like this. So if our incoming signal ran through these, we're sort of getting the highs over here, and we're getting the lows over here. And if we take some midpoint between those two, we're setting this threshold. Okay. And then if we run that into a comparator, then our output will be 1s and 0s depending on the signal. So this is sort of the idea of all of the circuitry here. It's a little bit fancier here, but this is kind of the basic idea. We'll just kind of stick with that. So one of the things that is a problem with peak detectors is you're losing all this signal. You're losing 0.6 volts going through these diodes. Maybe if you made them Schottky diodes, you're only losing 0.3 volts, but you don't want to lose any voltage at all. So we can, all right, if we want to build a peak detector that has no voltage loss, we can use an op amp, and we can run our signal into the plus. Here we have a minus. We can put our diode in to a feedback path, and this will make sure that the voltage here doesn't have any voltage drop. And then if we wanted to build a peak detector, we would put our capacitor here. And then if we wanted to build a negative peak detector, we would just change the polarity of the diode. Oops. And here we'll pick our threshold, and we can run that into another All right. So we need 3 op amps and some diodes and stuff. So if we look at this particular device, let's see. We have, looks like 2 op amps here. These are probably dual op amps, so we have 4. Trying to remember if this one was actually built that way. But it's similar. It's similar to this. So we do have a photo detector over here somewhere. We have a photodiode, and it needs to go into some type of amplifier. So there's going to be a some type of transistor out here, and there's some front-end circuitry here, op amp, transistor, right? And there's a bunch of things here, and since these things kind of varied a bit, the current through the LED is kind of critical to get this thing working right. Since these are a bit different in gain and everything, you sort of selected this resistor to make sure this all worked really well. So you can see this whole thing is a surface mount, except for this one through-hole resistor right here. And that resistor is this binning resistor where you get to set this thing. So these had to be adjusted in production. All right. So we've looked at the circuitry here. Let's take a look at a different model. All right, here's a model that's quite similar to this one. We have a piggyback board. In fact, we can remove this one, and we'll take a look at that in some detail. We have a nice big capacitor here. I think this one should have had a capacitor. There's holes for it. This one looks like it actually functioned at one point in time. On the back here, we have a quad op amp package here, and we have the other packages here. I think these are actually 555 timers in this one, and for various reasons, I don't want to go into that, but this thing actually pulsed the LED on and off. But you can see that this was all analog circuitry, and this was just the thing that made it into a stream of zeros and ones, and then this was the thing that actually did the decoding. So on the top here is an Intel 8051, or a version of it. Remember that the 80 series of microprocessors from Intel always required a demultiplexing of the address. Remember on like 8085 boards, there's always a chip that does the demultiplexing of the address lines, and sometimes it's a 573, which is a particular part. Here we have a 373, so this is doing the demultiplexing of the address line, so that's required. This is an 1K EEPROM, so you can store configuration data into a serial E2 PROM. And on the back here we have RAM, so there's no RAM, not enough RAM available in the 8051, so there's I think this is a 2K/8 RAM chip. It's a Toshiba 5517, a very classic chip. There's a crystal in this one, 11.059 megahertz crystal, and then a buffer chip. And that buffer chip was used to drive the RS-232 lines. It drove them at TTL levels, but usually you can get away with that. All right, so that's one particular generation of the chip. Let's look at a different generation. Here's a version that was done a few years later, and it's very interesting. If we take this piggyback board off, we can see a bunch of chips on this one, and in fact, the whole back half of the board is the same as this board. So this is all digital circuitry. This is microprocessor and RAM and all that stuff. And the front half of the board is all of the analog circuitry. and there's this big conspicuous chip. So all of this and all of this is the analog circuitry. And we sold these in enough volumes to justify doing a custom analog chip. So all of these transistors and op amps and everything all got put onto a single integrated circuit. So we've made it so it's much smaller now, but it's the same circuit. It did the same thing. And the back half of the same circuit, we have an E2 PROM, we have RAM, the microprocessor, we have the demultiplexing chip, and in this particular one we have a ROM chip also. So we have external ROM. So we have a bunch of things here, and then we have the crystal. This particular board here is particular to that photograph I showed you. This is the actual board that interfaces an IBM PS2 computer. So this is the circuitry that has an analog switch. It has a 4060, I think it's a 4066 chip. Where's the magnifying glass? Yeah, 4066 chip. It has a HC05 chip, so that's an open collector inverter, and it has an 04 chip, which is a inverter, and it's actually an HCT part. So the analog switch allowed you to switch between barcodes or keyboard, and then these two chips allowed you to interface to an IBM PS2. So you could run this board as is with serial data, or you could put a board on it, and it was meant to go together, and then this became the product that did the keyboard. All right, and then let's go another generation. So here's another generation. This is pretty nice. So this has the same functionality as this. So we've managed to take all of the circuitry that was on two PC boards and put it all onto one PC board. Again, the front half of it is analog with a custom chip, and the back half is all digital stuff. The microprocessor, you see, we've gone to a ceramic resonator instead of crystals, much more rugged. The EEPROM is now available in a smaller package, so we're able to reduce that. This is a RAM chip. This is the demultiplexing chip. And then these chips here are the chips that were on this piggyback board. So they all fit now. And I actually remember laying this board out. I was actually the designer that laid this PC board out. But yeah, we put a lot of things in a small space. This was back in the early 1980s, around mid 1980s, and surface mount was actually quite new. And there was a place in Hewlett-Packard that could do surface mount really well, and that was the calculator division. So we actually had this product. The PC boards were actually built with the robots at the computer calculator division up in Corvallis, Oregon. So again, really nice designs. Very, very state of the art back in 1985, 86, something like that. So I thought you'd be interested in looking to see the kind of the progression of how a big company actually designs products. They start with what they can do, and then they say, okay, now we can do a custom integrated circuit, and that will shove things down in size. We're able to get new parts. We're able to go to ceramic resonators instead of crystals. That's more rugged. We're able to get E2 PROMs in a smaller package. We're able to stuff more into a smaller spot. And in fact, in smashing things into a smaller spot, when you're working on projects for large companies, a lot of times there's code names, and you have these code names. And this particular code name, I don't know if you can read this, but it's PRNGL-80005. This was a prototype board, and the code name for this project was called Pringles, because Pringles put 2 pounds of potato chips into a 1 pound can, And that's sort of what we were doing. We were trying to put these all into a small can and getting the things in a small spot. So we picked the code name Pringles. So that's what this one is.